So let us go over a quick introduction to this class. We talked about the syllabus, and now we want to go over what is going to happen during this semester. So the first thing is that um, we're gonna have to review vectors again. The Most of you were in my class, so in statics, I mean. So you probably remember that in statics, all the summation of forces in X were equal to zero, and all the summation of forces in Y were equal to zero as well. We always defined a coordinate system, and in dynamics is going to be the same, but we're gonna go one step further. What that means is that we're gonna go over three very important laws, which are Newton laws of particles or systems in mechanics and dynamics. So we'll go into details, but the first law is about inertia, saying basically that a body that is at rest will remain at rest unless something else happens that makes it lose that state. The second law, which is very famous, is that the summation of forces on a system or a particle or a system of particles is equal to the mass of the particles times the acceleration. And here, let's take a look. So from statics, we know that the summation has to be zero, meaning that everything is going to be at rest in equilibrium. Could be deformed, could be in a tension, in a compression, but will be an equilibrium. In dynamics, all the summation of forces in a system in X and all the summation of forces in Y are going to be equal to the mass, which is going to be conserved in this equation, meaning that the mass, if the mass is 3 pounds, will remain 3 pounds. In this class, we're not going to see a change in mass. That will be more into that will be complicating things, because then you're going to have to take into take into account the change in mass. In this class, the mass will be constant. So the mass of an airplane will be the constant, the mass of a car will be constant, the mass of a ball will be constant, all right, times acceleration. So it's not zero anymore. In this class, we will have the summation of forces equals the mass times the acceleration. But remember, the forces are vectors. Mass is not a vector, but acceleration is a vector. So when we go back and review vectors, we'll see that if you have a vector A with components, um, I don't know, let's say A1 in I, A2 in J, A3 in K. Okay, I hope you remember this. If not, we're gonna have to review. You have a three-dimensional vector. Actually, we can add a fourth dimension, which is time. But for now, let's just say it's 3 dimensions in space, and X, Y, and Z. Okay, and we're gonna call this O, the origin, but also we're gonna start using O as the name of this frame of reference, because one of the things that you're gonna see in this class is that the coordinate system could change, could move, could rotate, as long as it's an inertial coordinate system. So we'll go over that. I know at this point you don't know what I'm talking about, which is fine, but a coordinate system has to be orthogonal. We know this by statics. Orthogonal is that all the axes have 90 degrees with respect to each other. I, J, K. and has to be an inertial coordinate system. We're going to have a whole lecture about inertial coordinate system. If it's not an inertial coordinate system, we cannot use it in our computations. Every coordinate system in dynamics has to be an inertial coordinate system, unless you're doing some special cases, which we're not going to go into the case that we're not going to go over special cases. We're going to go over the general law of inertial coordinate systems. We'll talk about that later. Now, the summation of forces is equal to the mass times the acceleration. Again, the mass is going to be constant. So for instance, if you, an example where mass is not constant, consider a tank of gas. The gas at time 0 has mass 0, some type of mass, some quantity. But after so many hours of burning or doing work, the tank will move to a state where the gasoline is M1. And obviously, M0 is greater than M1 because it's burning. So in this case, mass is not conserved. In this case, mass is not constant. So this is not something that we're considering. We're considering a ball where the mass is constant, or a star or a planet where the mass is generally more or less constant. So we assume it's constant. And that assumption cannot affect other things. All right. And the third law, again, we're going to go over the three laws of dynamics, or Newton laws, in detail. But basically, this means that a particle or a system that has a force over another particle is basically subject to the same force from the opposite particle. And that we saw in statics. For instance, when you have a box on the ground, the weight of the box is putting some force on the ground, but the ground is putting some force on the box. Otherwise, the box will lift, or the box would keep going down. But the ground is holding it steady, and the gravity is holding it from going up. All right, so that's the third law, that body that is subject to a force will be exerting the same force on the opposite body. Second law is forces on a system equals to the mass times acceleration. And the first law is the inertial law, where everybody that's at rest will stay at rest unless a force is applied to it. Okay, we'll have the right wording and the right details about these laws, but for now, this is an introduction of what we're going to see. So we're going to move from forces on a system equals 0 to forces equals to mass times acceleration. So talking about acceleration, you're going to be able to remember that acceleration is the second derivative of displacement or position. Okay? What that means is that if you have a position x, and again we're gonna go over details, but this is just an introduction. You have a particle x in space. All right, so origin x, y, z, and you have the particle x. That particle x is moving in a path in time. So this is time 0 and this is time 1. Think of this as a planet or a star or a ball, whatever you think, whatever you want, as long as you have a constant mass. So that trajectory in three dimensions, x, will have coordinates. Actually, this trajectory, let's call it L. L is a function of time, little x, little y, little z. To be completely strict, capital X, this capital X, is a function of little x, little y, little z. Basically, a function of coordinates, a function of space. 3 units in x, 4 units in y, 5 units in z, whatever. We saw this in statics as well. You can define this initial point as a vector with respect to O. And you can define that final point with respect to O with a vector. So L, this trajectory, is a function of the time that it took and the change in position. All right. So the velocity is a vector with the change of L with respect to time. Okay? And the acceleration will be the change of velocity with respect to time. Hence, acceleration equals the vector acceleration equals the change, the second derivative of the change of L with respect to time. All right, so this is something that we're going to go over in detail as well. But the acceleration is the second derivative of the position. Therefore, another way of expressing the summation of forces on a system is equal to mass times the second derivative of position with respect to time. And this could be x, or if you want, could be L. It's really depending on what you have your function defined as. If this is your particle trajectory, then it's the second derivative of this trajectory with respect to time. If you want to find that acceleration, then this is pretty much what we need. So you're going to see a lot of problems where they give you a function. And the function could be, I don't know, function with arguments x, y, and z is 2x t y in I plus 2y t squared in j plus 2y z t k. I'm just making things up. So you have 3 coordinates and they're functions of x, y, z, and time. So we have 4 variables. Luckily, we're gonna only deal at first with x and time, but you can have multivariable operations where it's all 3 dimensions and even more dimensions. You can have rotation, like radius, etc. But this is a 4-dimension problem. We express in 3 dimensions x, y, and z. X, y, and z, again, coordinate system is completely important. And the change of that, even change of that coordinate system to a new position. Okay, all this is just part of the introduction. So what changed here was that in time the position was different. So if you want to differentiate this guy, to find the velocities, so v equals df dt. Remember, f is a function of t, x, y, and z, but velocity is a function of time. Sorry, it's a change with respect to time. So we know how to do that. It is going to be 2x y in I plus 4y t plus 2y z. So we're just deriving here. So notice that our velocity is still a vector, and that's what we're saying. It's I, j, and k from this position I, j, and k. And I made up this vector, so this might not even have any real meaning, but I'm just telling you that the derivative of this position is the velocity. And interestingly, if you're going to do acceleration, which is the second derivative of f with respect to time, or the derivative of the velocity with respect to time, and the velocity is obviously a function of t, x, y, and z because it's a derivative of the function, then this derivative is no t here, 0I plus 4y j plus 0k, no t. So the acceleration is only 4y. Okay, so it's only accelerating in one dimension, in the y-axis. So we're gonna have to review how to deal with vectors, how to multiply them, how to add them. If you remember, you have dot product. If A is a vector, you can have dot product between them. You can just add them. You can subtract them if B is a vector or A. And you can have something called the cross product or the curl. Remember, all these things are things that we're going to have to review. And this is extremely important when it comes to rotation. In statics, we saw that you can do the curl to find the momentum. No, I'm sorry, the moment. Remember when we had force equals distance times length? If you had two vectors, you can do the cross product. Here in dynamics, you're going to have rotation associated with this guy. So we're going to have to review this concept as well. So we know by now that dynamics, we're going to have to deal with accelerations, and acceleration is a second derivative of position or a derivative of velocity, depending on what you're given. And right now, they're going to give us the function. But later, if you go into aeronautics or physics or engineering, you're going to have to decipher the function. You're going to have to design a control loop for a robot that is going to go in a path that is around a satellite or something. And this is a function. In that function, you're going to have to decipher what you need it to be, at what accelerations, what velocities, yes, all those things. You have right now it's going to be very easy, believe it or not, because the function is going to be given. But when you start working in your field, if you go for physics or aeronautics or engineering, you're going to have to come up with this function based on system of forces, on accelerations, on process that you need to control. So that is really the complicated thing. But we're going to use we're going to do back engineering. We're going to use those functions to learn the dynamics. Okay, so we're going to learn about rotating frames. So for instance, if you have, again, the X, Y, and Z, and this is my original frame, and then you have a particle A. Let's say this is the Earth, this is the space station, and this is a satellite. So the distance or the position A, remember from statics that you can define those distances as r of A with respect to O. So you can do that distance right here. Okay, let's say that then you want to know your distance from the space station to this satellite at this point. So that will be the distance of B with respect to A. And then obviously you're going to have a distance of B with respect to O. Okay. So at this point it would be pretty easy if everything's static. But let's say that the space station is moving, and the satellite is also moving, and the Earth is moving with respect to the Sun. So where do you keep your inertial frame? And again, we have to talk about what the inertial coordinate system means, but where do you put your coordinate system so that you compute the velocities? And this is an important concept, the relative velocities, because the velocity of A with respect to B is different than the velocity of A with respect to O. So those are relative velocities. So we're gonna learn how to formulate this this concept. And this is distance. If you do the derivative of our distance between B with respect to O, you that with respect to time, you're gonna get a velocity of B with respect to O. But how is that with respect to A, which is also having a distance? So picture A is moving, towards the moon, and B is moving around the sun, or sorry, B is a satellite moving around the Earth, and O is the Earth is moving around the sun. So all those things you can express accurately where they are at any position in time and space. The important aspect here is where you choose your coordinate system and how do you compute those velocities. So we're going to learn how to do that. All right. Later, we're going to learn about vibrations. It's going to be an interesting topic because think about your car. So your car has the chassis, all right, and then you have the tires. The tires have suspensions, and they're usually springs and dampers. Let's talk about that. And airplanes and strollers and most systems that you can think of, except for a table and except for a dishwasher, but dynamic systems have springs and dampers. So let's think about the car. So we have the car, and then we have the suspension, which is going to be a spring. And then let's say that, I don't know if you've noticed, but even a motorcycle or a bicycle or the car itself has something here which will prevent it from going up and down repeatedly, like vibrating. That's something that you want to avoid because you can get something called resonant frequency, and it will just start increasing in the vibration. To avoid that, you put a damping system, which is usually drawn like this. All right, and then you have your tire. All right, so let's say that we lift the car. You go to your dealer, they lift it, and they're gonna change the oil. They just do a simple case. It's not vibrating with time, it's just one simple lift. So there's something pulling up, and this has a weight. How do you express what happens here? Which is the simplest case I can think of, right? Because this is the car, the engine and everything, and this is the wheel. So you can choose your coordinate system more or less here. And at this point, you care about the forces. So remember, free body diagram. This is something that we're learning again, but we saw it already in statics. So from statics, you remember the springs have a constant, a linear range, right? If you apply a force, they have a linear displacement up until a point where they're not linear and they break. But we care about this linear range. A regular spring, not a fancy non-linear spring. We're talking about a regular spring. And the damping here is changing the amount of velocity at which this thing moves. So if you remember, the whole concept of this class is that we're going to build a system of equational forces, external forces, so that we can equate to mass and accelerations. Well, from our body diagram, we can do the tire has a weight, and then we have a force up. Remember, we're lifting the car, and the damping force. F damping and F spring. So let's go ahead and see. Let's do summation of forces. So we say summation of forces in Y. Actually, there's nothing in X right here. It's not moving, it's just lifting the car up. Summation of forces equal to 0. Summation of forces in X equal to 0. And that way is positive. And that's not interesting at all. But let's say summation of forces in Y equals mass times acceleration. Let's say positive up. So we have that F spring plus F damping minus the weight of the tire is equal to mass times acceleration. All right, so what is F spring? Is K times Y. Is the distance in Y. F damping is usually B, is a constant, and this could be pretty fancy. Could be a viscoelastic material, so it might not be a constant. Could be a function itself. Could be a function of time and a function of position, but let's not worry about that right now. Right now we're just introducing concepts. This is going to be by the end of the class. You're going to be able to do things like this. And damping, if you don't know by now, remember, this is the time to learn this and remember it. Damping affects the velocity of a dynamic system. So it's going to be the change of Y with respect to time. Now we're going to learn something here. dy dt is the same as y dot. This is pretty standard. Now, the difference between y dot and y prime is that this is y with respect to time, and this is y with respect to space. The y dx is y prime. The y dot is the y dt. And this is minus the weight of the tire, so m tire times gravity, this is an acceleration, remember, is equal to mass times acceleration. The mass of the tire times acceleration. So we're going to have dy squared dt. All right, so another way of showing this is, let's bring things to the right hand side. So my dot dot plus by dot, minus, remember that we have to take that to the other side, minus by dot minus k times y, which is just the spring, is equal to minus mass times gravity. Okay. So, yeah. Yep. So the gravity is affecting definitely the force down, and this mass has to do with how fast we're going up. Okay, yeah. So basically, if you don't see this very clear, this is m times dy squared dt minus b dy dt minus ky equals minus m times g. This right here is a second order linear differential equation. If you saw calculus, you already know how to solve this. This is a non-homogeneous linear partial linear equation. Partial linear differential equation. And the solution of this guy is going to be, you can look in your books, it's going to be exponent of the roots, and you already know how to solve this equation. If not, then go back to your calculus book. This class we're going to be able to write down, we're going to be able to derive these type of equations. And then we're going to see if we take a time perspective or a frequency perspective. Then we're going to learn a little bit about that and how vibrations affect this kind of thing. All right, so I hope that this is motivating, how this class is going to go from particles and systems that are moving into whole concepts of vibrations and rotating, moving coordinate systems and spatial. And this is why it's so important in space and aeronautics to know these things, because you can have relative velocities and compute relative accelerations.